I'm Alisha,
I'm Gabe.
And I'm Smear.
and this is our first logic project, which is on the tree test.
So today we're going to be talking about primarily the overview of functionality of the tree test. We're going to talk about what it is, the rules of inference which are inherent to it, and some examples of the test in action.
And then we're going to compare the tree test to the two other methods of formal proof, which are truth tables and natural deduction, and then we will look at the tree test in the context of decidability, soundness, and completeness. So, what is the tree test? So, the tree test is a method of formal proof which is guaranteed to determine the validity of an argument, and it keeps track of all possible cases, where each branch of the tree represents a specific case. Also, a tree test identifies specific cases as counterexamples if one exists, thus providing the argument as being valid or invalid. So the algorithm, or how does it work? So the first step of a tree test is to list the premises and the negation of the conclusion as a set of sentences. Then you list all possible sentences that have to be true given the initial set of sentences, or given that those set of sentences are true. So if there are more set of sentences that are true, then you list them vertically, or you list conjunctions vertically. Or if there are no conjunctions implied, then a disjunction follows, which involves an either-or situation. This also means that the tree will branch. So the next step is to keep branching the tree by using rules of inference until no further sentences can be decomposed. So this also means that a finished branch is one where all decomposable statements in that branch have been decomposed.
So earlier we mentioned that the tree test will determine the validity or invalidity of any argument. This is as a result of the decision procedure. So if an atomic sentence and its negation both belong to the same branch, we close that branch, symbolized here by an X at the base of it. If all branches are closed, that means that the initial set of sentences contains a contradiction in every case, because we said that each branch represents a given case. Therefore, the set of sentences which contains the premises and the negation of the conclusion has to be inconsistent, which is saying, in other words, that there is no case in which all the premises are true and the conclusion is false, which is the literal definition of a valid argument. Conversely, if a branch cannot be closed, that means that there is a case in which all of the initial sentences are true. So, the set containing the premises and the negation of the conclusion is consistent, thereby insinuating that there is a case in which all the premises are true and the conclusion is false. This case is a counterexample to the argument, proving that it is invalid. The tree test relies on a series of rules of inference. At the beginning, obviously, we can conclude that a branch can be closed if a contradiction is inherent, or we can remove a double negative. A conditional relies on the conditional disjunction to infer if circle then triangle. For the tree test, we conclude not circle or not triangle. They're placed horizontally, as Alisha mentioned, because it's a disjunction. These belong to two different branches. For a conjunction, we say circle and triangle, symbolized here by circle and triangle placed vertically. For a disjunction, we write them horizontally, representing, once again, the two branches representing two different cases. And for a biconditional, both of the antecedent and the consequent must have the same truth value in any case. Therefore, we write it in the tree test as a disjunction of two separate conjunctions. That means that both of them are true or both of them are false. And that is just symbolized in tree test syntax. A key quality of all of the rules of inference is that they break a complex statement into its atomic components always, because the goal of the test is to reduce an argument to the truth values of its atomic sentences in any given case. This utilizes the equivalence of the conditional disjunction, De Morgan's laws, etc., which we derived previously in natural deduction setting. So, from any given statement with a connective, a conjunction or disjunction can always be drawn, symbolized by the branching of the tree as vertical or horizontal. So rather than inferring other complex statements from statements guaranteed to be true, as is the case in a natural deduction proof, the tree test relies on deriving the fundamental case nature of an argument and bringing it down to its most basic form.
Okay, so now we're going to look at some examples of the tree test. So for our first example, we're going to look at this argument. I have already said that he must have gone to Kings Pyland or to Mapleton. He is not at Kings Pyland, therefore he is at Mapleton. So on the left you have the two different atomic sentences, and on the right you have your premises and your conclusion in standard form. So here's the tree test for this argument. So first you list the premises, which are K or M, and not K, and then you list the negation of the conclusion, which is not M. So Given that K or M is a disjunction, or your first premise is a disjunction, you can branch the tree out into K or M. Because the K branch has a contradiction from your second premise, which is not K, this branch closes out. And your M branch has a contradiction from your negation of your conclusion, not M. Therefore, this branch also closes out. Because there is a case in which the premises and the conclusion are true, this argument is valid.
Here's another example. The patient will die unless we operate. We will operate, therefore the patient will not die. We can see the atomic sentences on the left side of the screen here, and we have on the right side of the screen, we have the arguments in standard form. So drawing a tree test, we have this initial set of sentences, which include the premises, and the negation of the conclusion, which is D. And because using the first premise, which is if not O, then D, by the rules of inference, we can infer the branches O and D. Because there exists no contradiction, both paths remain open, and thus the argument is invalid.
Moving on to a slightly more complex example with 3 atomic sentences, we state that if Adams wins the election, Brown will retire to private life. If Brown dies before the election, Adams will win it. Therefore, if Brown dies before the election, he will retire to private life. Obviously, ignoring the questionable soundness of this argument, we seek to examine its validity here, and we summarize it in standard form as follows. Drawing out a tree test, we list the 2 premises and the negation of its conclusion. From the negation of the conclusion, we infer D and not R must both be true in any case for this statement to hold. From here, we utilize the first premise to branch out into 2 cases in which not A or R is true. This follows, and as R clearly contradicts the previous statement, not R, we close that branch and move to the left side, where from not A, we utilize the second premise to branch into not D or A. As is clearly shown, not D and A both contradict previous statements that we've concluded to be true, thus closing both of those branches. This argument is valid because all branches are closed and the set is inconsistent. Example 4. If I'm right, then I'm a fool. But if I'm a fool, I'm not right. Therefore, I'm no fool. Summarized in standard form at the top and the tree test on the bottom, we infer from the negation of the conclusion into 2 branches from the second premise, not F or not R. Because not F directly contradicts F, we close that branch and move to the right side, not R. We branch here into not R or F, both derived from the first premise. Because not R and F both fail to have any contradictions inherent to the proof, we conclude it must be invalid because of the openness of these 2 branches.
Okay, so now to compare the tree test to the other 2 methods of formal proof, the first of which being truth tables. So something similar between these 2 methods of formal proof are that they both have decidability, which means that they both terminate. Something different is that a truth table finds every truth value, and after 3 variables, it does get a little bit tedious, whereas the tree test is a lot more efficient because it looks for a specific case. Also, it can handle arguments with a very large number of variables and is a little bit more similar to the way people reason. Because of this, a tree test is a bit more ideal for computation for large arguments because the truth table is so memory intensive. Also, the structure of a tree test is more akin to natural human reasoning because humans usually don't look at every single possible truth value of an argument when they are trying to make a decision. So now looking at the tree test versus natural deduction. So something similar between these 2 is that they both have rules of inference, but the tree test rules of inference do overlap a little bit more with the natural deduction's logical equivalences. Another thing that's similar is that both of these methods are a little bit similar to informal proofs, but the tree test is similar to informal proof by contradiction, where you assume the negation of the conclusion, whereas a natural deduction is similar to that of a conditional, where you conclude the truth of a conclusion given the truth of the premises. Something else is that a natural deduction is a little bit more similar to the way people reason because it overlaps a little bit more with common sense, such as the hypothetical syllogism. One huge difference between the natural deduction and a tree test is that a tree test has decidability and natural deduction does not. This is because natural deduction will not work with invalid arguments. If you input a invalid argument into natural deduction, you will get nowhere. This also means that the tree test is a lot more ideal because of this, but despite this, natural deduction is a little bit more instructive because it is a lot less complex than the tree test.
A test has decidability if it terminates. So we can see this with natural deduction, that natural deduction does not have decidability because it will never terminate if the argument is invalid. On the contrary, we know that the tree test has decidability because the test does terminate for both invalid and valid arguments. The only exception for this is if there exists an unlimited initial set of premises. So let's try to prove this. So let's say we have an initial set of sentences containing premises and the negation of the conclusion. Using the rules of inference, we can use each initial sentence to make branches. If a path remains open, we can use the rest of the initial sentences until we can close the path. If all the paths close, then the argument is invalid. If even after using all the initial sentences, at least one path remains open, we know that the argument is invalid. A test has soundness if it never calls a consistent set inconsistent or a valid argument invalid. So let's assume that there exists a case where all the premises are true and the conclusion is false. This means that the set of sentences containing the premise and the negation of the conclusion are all true and thus consistent. Because the set of initial sentences are consistent, all the following lines that are derived via the rules of inference are non-contradictory and remain open. This guarantees that at least one open path exists in the tree if the initial argument is invalid and the initial set of sentences are consistent. A test has completeness if given an inconsistent set of sentences, the test will always show that the set is inconsistent. So assume that there already exists an open path. This means that no contradictory lines exist thus far. If these lines are determined from the set of initial sentences, we know that there exists a case where all the initial sentences are true, meaning that the set containing the premises and the negation of the conclusion are consistent and that the argument is invalid.
In conclusion, we'd like to begin by summarizing the basics of the tree test. First, we state that the test uses the consistency or inconsistency of the set of premises and the negation of its conclusion to prove the validity or invalidity of an argument.
To reiterate, closed branches or an inconsistent tree test means the argument is valid.
Open branches or consistent tree tests mean that the argument is invalid.
Additionally, we noted that the tree test involves rules of inference, which are similar to those of natural deduction, but slightly different.
Additionally, the tree test is able to handle very complex arguments with large numbers of variables and is the most efficient method of formal proof, despite it being less instructive than natural deduction and truth tables.
So overall, the tree test has decidability, completeness, and soundness, suggesting that it is an optimal method of formal proof. We hope you enjoyed our presentation, and we thank you for listening.